Okay, done. So now technically I believe today we will finish up chapter 2. This I'm still here. Is anyone accidentally clicking mute? Alright, so now there's no notification. So I think you can hear me. Anyways, there's one more thing in chapter 2 which I'm not sure whether I want to cover it or not. Let's see how it goes. But for today, I already have an aim on what I want to cover. Okay, so one thing which is called conservative vector fields and scalar potential. The name sounds so complex and complicated, but the thing inside it is not that complicated. It's okay, Yizhuan, it was you who muted me. Our class test, that's the next thing I wanted to talk to you about. How about next week? Next week, because I don't know how's our timetable will be, but let's fix it in this way. Next week, our second class. Are we having two classes? Sometimes our lectures are separated. Sometimes it's together. But let's keep our class test for the second class, whichever that falls afterwards. Because if I see the first class and then suddenly the first class falls on Monday, it might be too much of a rush. So let's keep our class test for next week's second class. Once the timetable is out, I will give you a more accurate detail on it. Our class test won't be testing both the chapters that we learned, only one chapter. Class test 1 will only be on multiple integral. That's that. Okay, multiple integral. For your class test 2, which will be on a later date, okay, once we are done with this, we can focus on class test 2. That will be on chapter 2, the thing that we have just learned so far. Anyways, without wasting any time, let us get on the thing that we want to cover for today. Let me share my screen. Okay, so here we go. Let me know if you have any problem viewing my screen or hearing my voice. Okay, we can sort that out. Otherwise, this is the thing I wanted to cover for today. Conservative vector fields and scalar potential. So take a piece of paper. There's quite a bunch of calculations involved in this topic. The first time you are hearing it, it might seem like a bit too much, but then hopefully with a few more practices, it gets a bit easier. So let's go with what is a conservative vector field and what is a scalar potential. And from there, we'll work around on how to do questions involving conservative vector fields and scalar potential. First thing first, this definition right here. If there exists a function f such that this whole thing is true, then you have a conservative vector field and a scalar potential. The statement might not be that direct. You might be confused, what does it even mean? It means that if you have a function, okay, such that the gradient vector of that function, do you still remember gradient vector? Gradient vector is something like in this form. Oh my god. Okay, you have fx, and then you have fy, and then if you have z, there's going to be a third component as well. But let's say you only have two components, so fx and fy. Okay, and this is a vector, right? So this is a vector. Let me denote it by this big F. So if I give you any vector, let's look at the reverse version of it. Instead of starting from here, let's start from the vector. If I give you a vector, and then you manage to identify that there exists a function f such that the gradient vector is actually that vector. If this is true, then this vector here is called a conservative vector field. Okay, meaning that when I give you a vector field or a vector function, it means the same thing. When I give you a vector function, if you can find a function such that when you find the gradient vector, you get back this capital F, then it means this vector is a conservative vector field. And the name given to this small f, the name given to this is a scalar potential, also known as potential function. I used to call it potential function, but since I teach engineering maths, I see that all the engineers or all the textbook call it scalar potential. So now I call it scalar potential as well. But when I first learned this, when I was studying, I call it a potential function. So it doesn't matter, scalar potential or potential function is the same thing. Okay, so that is by definition. Now, so it all starts with a vector function. From a vector function, you can determine whether the vector function is conservative or not. And if it is conservative, then you should be able to find the scalar potential. That is how the flow goes. Okay, so as usual, instead of explaining it in a more general form, I prefer an immediate example. The first thing, there are two parts to this. Whenever I give you a vector function, you should be able to tell me whether the vector function is conservative or not. And if it is conservative, second part, you should be able to find the scalar potential. If it is not conservative, there's no even such a thing called scalar potential. So you stop there. Okay, but if it is conservative, you can further find what is the scalar potential. Okay, so that's how it works. And the most common way of determining whether a vector field is conservative or not is this test right here. This is your test. Dou P over dou Y is equal to dou Q over dou X. Let me elaborate a bit on this. This is assuming that when I give you a vector field, right? I give you a vector field. Assume that that vector field or vector function, whatever you call it, is in this form. You have a P and then you have a Q. It's just a variable assigned to the first component and the second component. So you look at these two components. What you do is you differentiate the first component with respect to Y. You differentiate the second component with respect to X. If both of them give you the same answer, then it is conservative. That is the test. If even it changes, even if it differs slightly, maybe this one is a +1, this is a +2, done. It's not conservative. If they are exactly equal, they are conservative, then it is a conservative vector function. So let's do an example here. So I have a vector function with me right now. I do not prefer to write it in this way, but the online website that I took the example from, they write it in this form. So let me write it in a form that I prefer. Prefer this. So you have 2x cubed y4 plus x, and the second component is 2x4 y cubed plus y. Okay, I prefer this. So once you have the vector in this notation, the first part is what we identify as the P. The second part is what we identify as the Q. So you have a P and a Q. So let me find my dou P over dou Y and dou Q over dou X. Let me see whether they are equal. So if I differentiate P with respect to Y, remember partial derivatives, if you differentiate with respect to Y, all your X are constants. So my X cube is just a constant. So if I differentiate this, the 4 bring it in front, 4 times 2 is 8. So 8x cubed y cubed. X is just a constant, you differentiate constant, you get 0. So that's that. Now dou Q over dou X. So now my Y is a constant. If I differentiate this, the 4 bring it in front, it will become 8x cubed y cubed. Y is just a constant, you differentiate with respect to X, 0. So this is my dou P over dou Y and dou Q over dou X. I see that both of them are equal. I get the same answer. So my conclusion, because I get the same answer, is that the vector field F or vector function F is conservative. I haven't found the scalar potential yet, that's another story. But for the moment, I concluded that it is conservative, okay, by finding the two derivatives here. So let me zoom out a bit in case any of you want to digest a bit what is going on here. Let me know if you have any problem. I'll be looking at the chat from time to time. But otherwise, this shouldn't be that confusing. Just find the two derivatives, equal, conservative. Not equal, not conservative. Done. I don't know why I even use the blue marker, usually I use red. Remember that testing for conservativeness is just one part of the main picture here. The more important part is to being able to find the scalar potential. That is the next part we are going to look at. Okay, don't see any questions, so I think it's okay for me to move on. Let me know if there's anything. Okay. This. Now, we already concluded it's the same vector field, in case you're wondering. It's the same vector here and here. I use the same example. We have already determined that it is conservative. Now, because it is conservative, you should be able to find what is called as the scalar potential. The process to this is a bit long, okay, so try to follow along here. Again, assuming that your gradient vector is P and Q, okay, that is your gradient vector, or in other words, this is your vector field. Okay, vector field or gradient vector, both of them are equal because it's conservative, right? So maybe using this might seem a bit confusing for you. Let me just write F. Although when it means conservative, it's the same thing. Okay, so assuming your vector is in this form, and assuming that you already done the part where you have to check whether it's conservative or not, the next part is to find your small f, your scalar potential. Big F, vector function, small f, scalar potential. Now, you might see there are two small f here. The reason is because there are two ways for you to arrive at the same conclusion. There are two ways you can find what is your scalar potential, the first one and the second one. Both of them will give you the same answer. Okay. Now, first thing first, let me rewrite my vector function in this form. 2x cubed y4 plus x and 2x4 y cubed plus y. Okay, the easiest way I can put this is like this. This is your P, this is your Q. I can start from P and then I argue, and eventually I go to Q. You will see what I mean in a few more minutes, and then get the answer. Or I can start from Q, argue, and then go to P and get the same answer as well. It works both ways. So I'm going to try one of it. I'm going to start from P, and then I want to eventually go to Q and finally get the answer. Okay, I'm going to do one way first. All right. The idea is this. If you want to get the small f, the scalar potential, what you do is you integrate the P part here with respect to x. So 2x cubed y4 plus x, integrate it with respect to x. Because you are choosing the first component. The first component corresponds to x. If I start from Q, I will integrate everything here with respect to y. But right now I'm not doing this part. I just want to mention it. Okay, so right now I'm doing the first component. I'm starting from P and I'm going to end up at Q. Okay, so starting from P, I'm going to integrate my P with respect to x. So doing this, let me just cross check with the one that I did before the class to make sure I don't do any mistakes here. If I integrate this with respect to x, integrate with respect to x, your y is a constant. Okay, so it will be 2x4 y4 divided by 4 plus integrate this with respect to x, you are going to get x squared plus 2. And we would put a plus c. This is the common way. But in this case, you must take note of this. As I said just now, because you are integrating with respect to x, when you integrate with respect to x, your y is a constant. Your y is a constant. So why you want to write c when you know that your constant is in terms of y? It can be in terms of y. So I'm not sure, maybe my constant is y, maybe my constant is y squared. Maybe my constant is y square plus ln y, I'm not sure. But my constant is containing some y. So because that I'm not sure, let me just write it as a function of y. That's it. Because I'm not sure what is the exact form. All I know is that the constant contains some y. So just leave it in this form. So it looks like we already get our answer. This is my scalar potential. But not yet, because you don't know what is your hy. No idea for the moment. So this is where I'm going to Q. Okay, look what happens. If this is what I call as my first step, my second step, I'm going to differentiate whatever I get here. Okay, keep that in mind. With respect to the opposite variable. Just now, I integrated with respect to x. So now, I'm going to differentiate with respect to y, the other variable. So I'm going to differentiate f with respect to y. So okay, from here to here. Differentiate this with respect to y. You bring the 4 in front, the 4 and 4 cancels off. So what we have is 2x cubed, 2x4 y cubed. Differentiate x squared over 2 with respect to y, the whole thing disappears because it's just a constant. Differentiate hy, what would you get? You will get a h prime y. Differentiate h, you get h prime. Makes sense, right? Mathematically. Now, once I differentiate, I am going to compare. I'm going to compare with the thing that I did not touch just now. I started from P, right? So I'm going to compare with Q, the other part. So I'm going to compare with Q. My Q is this, 2x4 y cubed plus y. So this is my Q. Now let me compare side by side, okay? The answer that I get, 2x4 y cubed, 2x4 y cubed. H prime y, y. So just by comparing, I managed to conclude that h prime y is equal to y. Okay, just by comparing left and right. 2x4y cubed, 2x4y cubed. H prime y, y. Now, if this is true, if my h prime y is y, what is my hy? From prime, how do you get back the h? So what is hy again? Is it the same as c? Yes, it is the same as c. But we don't write c because we know the constant might contain some y. There might be a bunch of y there. So that's why instead of c, we write as hy. Okay? It's almost the same as c. So if h prime y is equal to y, then hy is equal to, alright, you're welcome Felix. Then hy is equal to integrate y, you get y squared over 2 plus c. The whole process of me doing the second part is because I wanted to know what was my hy in the very beginning. So I differentiate, I compare with q, I found out that h prime is equal to y. From there, I managed to find out what is my hy by integrating this with respect to y. So this is apparently my hy. Okay. So now that I know what is my hy, let me write back the whole solution completely this time. Okay, so I already know what is my hy. So my final answer is the scalar potential fxy is equal to 2x4 y4 over 4 plus x squared over 2 plus hy. What is my hy? It's y squared over 2 plus c. If I can simplify, I will. So in this case, the 2 and 4 can cancel off. So 1 over 2 x4 y4. Sorry about that. 1 over 2 x4 y4. 1 over 2 x squared. 1 over 2 y squared plus c. This is my scalar potential. A long process, but I break it down into two parts. The first part, just integrate the first component with respect to x and get your scalar potential. But you will realize that your scalar potential is incomplete because you don't know what is your hy yet. So the second part is dedicated to find what is your hy. How do you find it? You differentiate with respect to the opposite variable, compare it with the other component, and then you will get your h prime. From your h prime, integrate, you will get your h. Once you get the h, just put it back into here and write your final answer. Okay, it's a bit long, I know, but it's a standard procedure. No matter what function is given to you, this procedure is going to remain the same. So let me zoom out a bit. So this was the question, this was the vector function, and this is the scalar potential. Okay, so take some time to look what is happening here. If you think it's doable, I'm going to give you something to try out now. Take a piece of paper, try to repeat back the whole procedure that I just did, but now I started from P and then I go to Q, right? What you do is try to start from Q and then go to P, meaning that your first step will be something like this. Because I want to prove to you that you will get the same answer whether you start from P or you start from Q. So your first step is going to be fxy is obtained by integrating the second component, which is 2x4 y cubed plus y. Okay, if I choose the first component with respect to x, but if I choose the second component, then with respect to y. So this is going to be your first step, and then everything else, try to follow the step that I just did before this. So try it out. I will show it to you how it's done. But disclaimer, you will get the same answer. You must. If you get some other answer, something is wrong somewhere. Okay, so try it out. Take some time and try this out. Yeah, so I think you can see everything. Okay, so start from here. It's okay if you get stuck. Just let me know if you need some help. So if you're doing it, just remember that one part later, instead of adding C, you won't add HY because the constant here has to be of the opposite variable. So if you start from Q, you will be adding a HX. Okay, it's like the opposite of what we just did just now. Okay, just wanted to remind you that. If you're doing it, please continue doing it. But I just want to know whether you can get the answer or not. So let me just put a quick one. So if any of you are done, then you can just answer this poll so I can know roughly how much of you can get the answer. But if you're still doing it, please carry on. Nice, 15 of you did get the same answer. Okay. I thought it would be a bit hard for you guys to understand when I'm explaining it here, but apparently all of you get the same thing, which is good. And don't worry to answer no if you can't get the answer. I'm not going to call out your name or whatsoever. Just wanted to know if any of you are having any problems. Perhaps I think it's safe to say that the majority can get it, although some of you might have faced some problems. So either you get it or not. Let me just repeat the steps very quickly so that you can see if my working and your working differ anyway. Sorry, differ anywhere. So if I start from y, okay, let me just integrate this with respect to y. I'm going to get a 2x4 y4 over 4. Integrate y with respect to y, you'll get y squared over 2. Not plus c, but with plus hx, because x is now a constant. So now, I'm concerned on what is my hx. So therefore, for my second step, I'm going to differentiate everything, my goodness, with respect to the opposite variable, which is x. So I would get, let me just check, am I doing it correctly? Okay, I would get 2x cubed y4 plus, differentiate this, it disappears. Differentiate hx, you will get h prime x. Okay, so this is when I find df, dou f over dou x. And I'm going to compare whatever that I get with the letter that I did not choose just now. So compare, I started from q, so I'm going to compare with p. So when I compare with p, I see that my p is 2x cubed y4 plus x. 2x cubed y4 plus x. So comparing side by side, 2x cubed y4, 2x cubed y4. H prime x, x. So I conclude that my h prime x is equal to x. So because of this conclusion, I don't want h prime. I want h, just h, without any prime. So therefore, in order to get hx, I just have to integrate x, and therefore I would get x squared over 2 plus c. So because I already know what is my c right now, and what is my hx right now, so let me just plug in my hx here, giving me the final answer of fxy is equal to, I'm just going to rewrite back the thing that I got up here, 2x4 y4 over 4 plus y squared over 2 plus my hx is x squared over 2 plus c. Okay, so this is the same answer. Of course, the order changes a bit. Here I get x squared first and then y squared. Here y squared first and then x squared, but that doesn't matter. Okay, that is just a rewriting of the equation. It's the same process. First step, get the scalar potential. Second step, identify what is your hx or hy. It should be doable. And now, of course, most of you did get the two answers here. But how do we know that the answer that we get is indeed true? You don't have to do this part that I'm going to explain now, but just to convince you that indeed your answer is true, I want to show you that the answer that you get, the scalar potential that you get, indeed, according to the definition of conservative, do you still remember? The definition is that the gradient vector is equal to the vector function. So the vector function that we get should be equal to the gradient vector of whatever function we just arrived. So let us try to find the gradient vector. Gradient vector is the vector containing fx and fy. So differentiate, this is just checking, you don't have to do, but I want to do it to convince you that your answer is true. So fx, differentiate this with respect to x, you would get a 2x cubed y4. Differentiate this, 0. Differentiate this, you get x. Okay. Your fy, you differentiate this with respect to y, you will get 2x4 y cubed. Differentiate this, you will get plus y. Differentiate this, 0. The c, of course, 0. So this is what I get for the gradient vector. Let us compare with the vector function initially. Oh my god, it's too far. Can I bring it here? Okay, let me bring it here. Okay, let us compare. Yeah, indeed both of them are the same thing. 2x cubed y4 plus x, 2x4 y cubed plus y. See, when you arrive at the correct scalar potential, when you find the gradient vector, you will get back the vector function initially given. That's how you know you are on the right track. Okay, but this is just a checking. Again, you don't have to do it. Let me push it back. Okay. And yeah, there you go. Alright, so the time now is 1:27. Let's meet back at 1:35. I have no more new things to cover, but I want to give you two questions and then call it a day. Okay, so we gather back at 1:35. Okay, to do two questions related to this. So you can have your break, or you want to stay here, go ahead. But 1:35 we gather back. I'm going to stop sharing my screen for a while because I want to download something, a question. All right, the time is 1:35. Is everyone back? We're not going to continue any new thing, but I want you to do. I changed my mind. From two exercises, I think one is enough. One exercise that consists of everything, so you can try it out. Okay, Tanish is here. Yep. The rest of you are in the meeting, although I'm not sure whether you're far away from your laptop or not. But okay, so assuming everyone is here, let me share my screen. Okay, so this is the question that I want you guys to try it out. I give you a vector function. I want you to determine whether it's conservative or not. If it is conservative, I want you to find the scalar potential. So there are two parts to it. One question combining the two things that we have learned. So try this out. Let us discuss the final answer in a while. Meanwhile, I would really appreciate if any of you can do the solution and upload it. Okay, to make sure that at least one of us can do it completely. Okay, just let me know if you can do it. If you have any problem, let me know as well. But here you go. One vector field, determine whether it's conservative or not, and then find the scalar potential. So let me know what you think about it. Is F conservative or not? Okay, just fill up the poll. in any case, if you feel it's not, if you conclude that it's not conservative, then you can't even proceed after that. Okay, if it's not conservative, stop. There's no scalar potential for it. But if it is conservative, then you should proceed. Okay, we have an 8 to 2 with no leading the pole. (12 to 2), still no leading the pole with quite a big margin there. The 16 of you must have been confused. How on earth did the 2 felt that it is conservative, and the 2 of you would have been confused how 16 of them is telling that it is not conservative. So, alright, so while you are filling up the poll according to what you get for the moment, let me just try to work it out here. Okay, the meaning of conservative. Conservative, there's a test just now, where we remember the test was something like this. If you already know your P and you already know what is your Q, if your dou P over dou Y is equal to dou Q over dou X, then it's conservative. Otherwise, it's not conservative. So let's just find one by one. We have a dou P over dou Y. Okay, let me try to compute this. Okay. Differentiating with respect to Y. So 2x is just 2x, it's just a constant. E to the power of xy, if you differentiate, you will get e to the power of xy again. But you have to multiply some more with x, right? Because if you differentiate e to the power of 3y, you will get 3e 3y. It's the same thing here. Here you multiply by the 3, here you multiply with the x. Right? Okay. Give me a moment. Anyways, so plus with, if you differentiate this with respect to y, now this is a bit problematic because here you have one y, here you have another term containing y, two terms containing y side by side. Immediately product rule. Okay, so you have a u and you have a v. So u v prime plus v u prime. U v prime, okay, v prime, if I differentiate e to the power of xy, I'm going to get e to the power of xy again times x. Okay, uv plus v u prime. Differentiate x square y, you just get the constant, which is x square. So can I simplify this? This is going to be 2x square exy. This is going to be x square with another x, x cube, y exy, plus exy. Okay, let me just write it as x first, x square, exy. Okay, am I done here? No, I can further combine x square x square ey. So add them, there's 2 here, there's 1 here. So 3x square exy plus x cube y exy. So, it was a long process, but there you go. That is my dou p over dou y. So, of course, I have to check now with my dou q over dou x. Differentiating q with respect to x. Again, you must use product rule. There's a x here and there's a x here. So, u v prime is this. If you differentiate exy with respect to x, so it's going to be exy again, multiply by the constant, which is y. So u v prime plus v u prime. Differentiate x cube, we get 3x squared. Plus differentiate 2y, there's no even x there, so it's just 0. Okay, so can I simplify this? This would become x cube y exy plus 3x square exy. Is it the same? 3x square exy, 3x square exy. X cube y exy, x cube y exy. They are the same, right? Might be a bit long, but they are equal. So your conclusion should have been that it is conservative. I'm going to leave it here. Try to look where it differs from your differentiation. Okay, it's kind of tricky because the moment you feel this is not conservative, you will stop because it's impossible to find the scalar function. But in this question, you shouldn't stop because it is actually conservative. So just try to see what is different from yours. Product rule U prime is 2x. Wait a second, this is product rule for the first part or the second part? Which one? The first part, okay, let me see, the product rule. Okay, here I didn't use product rule, it's here. So this, for a moment, let me recheck. This is my U, V prime plus V, U prime. So you are asking about U prime. Okay, wait a second, U V prime plus, did I do wrong? Oh, no. Because Tanish, your U is this, right? Your U is x square y. That is your U. So if you differentiate x square y with respect to y, it's like as though you're differentiating 6y. You differentiate 6y, you get 6, the constant in front. So you differentiate x square y, you get the constant in front, which is x squared. Because it's inclusive of the y here. The v is usually an infinite value, the v. What do you mean by infinite value, the v? You mean when we are using the product rule, the choice of v? Not so sure about the infinite value. Oh, I see. If you keep differentiating, it doesn't end. No, not really. Actually, in product rule, maybe you are having some other v in thought because we also use v in integration by part, this and that. But for your choice of u and v in product rule, it doesn't matter. Actually, whenever you have two things side by side, let's say, just let me cook up a random example. Okay, just say, this can be your u and v, or this can be your v and u. At the end of the day, you are going to get the same answer. So not really. Just choose one of the product to be u, another to be v. But maybe the one that you are talking about maybe is another v. Okay, all right, no problem. So anyway, since you already concluded it is conservative, find out what is the scalar potential. Okay, last thing for today. What is the scalar potential? Remember, scalar potential, you can start from P and then compare with Q, or you can start from Q and then compare with P. If I am at your place, I would most probably start at Q. Because I see Q seems a bit shorter, seems a bit simpler to start with, compared to here there's too many things around. But that's just my preference. If you want to continue from P, go ahead, right? If you're finding the scalar potential, I actually did it while you're doing it just now. Let me share the final answer that I got and see whether your answer is the same as mine. For the scalar potential, okay, so I get a fxy is equal to x square e to the power of xy plus y square plus c. This is what I got. So let me know if you get something different, then I'll check mine again. Alright, so how many of you did indeed get the final scalar potential as in here, or you can't get it? Let me know so that we can proceed if there's any problem. Okay, so Chan managed to get the answer. Nice. How about the others? Okay, Dinesh, are you somewhere in between? I mean, somewhere along the solution, or you're unable to start from the very beginning? Okay, a few of you can get it. Nice. Okay, somewhere in between. Okay, I'm not sure whether you started from P or Q, but before I end the class, maybe just I'll show it to you how I did it. Okay, I started from Q, not because the other way around won't work, but I prefer Q. Okay, you started from Q, nice. So that will be the same as mine. So when I start from Q, it means that my scalar potential is what I get when I integrate Q, xq exy plus 2y with respect to y. You integrate p with respect to x, you integrate q with respect to y. So doing this, let me see, what do you get if you integrate this? X is just a constant, so we'll get back the same thing. Exy, if you integrate, you're going to get exy again, but you have to divide by x. Remember, if you integrate e to the power of 2y, it's going to be e over 2y again, but over 2. So same concept here. And then for 2y, 2y if you integrate is going to be y squared over 2. So the 2 and 2 cancels off, just y squared. And of course, we don't add a c, we add the opposite variable, hx. Almost done, but right now we are unsure what is our hx. So my second step is I'm going to find out what is my hx. So I'm going to differentiate everything that I got on top here. So df over, if I integrate it with respect to y, I'm going to differentiate with respect to the opposite variable dx. So let's see. Okay, first thing first, this x and x can cancel off. So it becomes x squared. It's a bit messy, isn't it? Let me write down nicely my function first. So my function is x squared exy plus y squared plus hx. Okay, anyways, I differentiate this in my second step. Dou f over dou x. Okay, let's do this. If I differentiate this, I have to use product rule, isn't it? Because this is my u, this is my v. So using product rule, u v prime is exy times y, because I'm differentiating with respect to x, plus vu prime. So plus v, my u prime is 2x. Okay, differentiate hx, obviously you are going to get h prime x. So let's simplify a bit. X squared y exy plus 2x exy plus h prime x. Now, because I started from q, I'm going to compare it with p. Okay, comparing with p, let me look back at the p. Okay, x squared y exy, x squared y exy is there, 2x exy, 2x exy is there, h prime x, there's nothing. These two terms are already here, so h prime x is nothing here, nothing as in 0. So in this case, when I compare, I found out that my h prime x is 0. If h prime x is 0, then hx, you integrate 0, you just get a constant. That's it. Just a constant. So that's why I'm going to conclude that my final answer for my scalar potential is whatever function that I get on top here, but now I know that my hx is c. So that means x squared exy plus y squared plus c. So that's how it works. Again, same step. Integrate, and the second step, find hx. If you started from P, any of you just now, I think you must use integration by part. But at the end of the day, no matter how you do it, you will arrive at the same answer. You will always arrive at the same answer. So the time is a beautiful 2 o'clock and I don't have anything else to cover. That was my aim for today. Conservative vector field and scalar potential. So before we call it a day, do any of you have any questions that you want to ask? Okay, I feel like there's no question. Should be fine. I will be sharing the whiteboard so you can have a look at it again. Class test next week, right? Next week on our second class. What is it? I started at Q but integrated with respect to X. Ah, I see. So no wonder you get a different thing. Okay, just remember after this, starting with Q with respect to Y. Started from P with respect to X. How long and how many questions? Harish, you did the same mistake as Dinesh, is it? As for the class test, two main questions, but the two of course have a bit of branches there like 2A or 2B. And how long? Usually when we do face-to-face, the class test is 1 hour. So for online, I'm going to give you 1 hour 30 minutes. So-called the 30 minutes is for you to upload the solution, this and that. So 1 hour 30 minutes, two questions with some branches, 2A, 2B, 2C and so on. But it won't be too long until it's impossible, no worries about that. How h prime x is equal to 0? Because Tanesh, I compared my whatever that I get here. Am I using a green pen? No. I compare whatever that I got here with my P. So I know it's kind of not obvious. Okay, let me go full screen for a while. Alright, so you can see that my x square y exy is similar to this. My 2x exy is similar to this. So my h prime has nothing, there's nothing else to compare. So the only way h prime x is actually equal to 0 because I have no other terms to compare with. Okay, the test, I'm not sure, maybe I conduct using Teams, maybe I use Microsoft Forms, but no matter what method I choose, I will give you a trial before that for you to upload the solutions. So no worries about that. Most probably high chances I'm going to use Microsoft Form because Microsoft Form you can upload your solution by questions, so easy for me to mark later on. Why do we do not integrate e to the power of xy? Jovian, which one are you telling me now? Exy. Why we do not integrate the exy? Okay, I'm going to take a wild guess here. Exy, is this the exy you're referring to? I mean, as in this exy, is that it? Let me know if I'm referring to the. Okay, nice. So that wild guess was correct. We did integrate Jovian exy. Actually, what we did was we integrate the whole thing with respect to y. So x cube is just a constant. It just sits in front there. Exy, if you integrate, you're going to get exy again. But exy over x. If you can't see why this is true, imagine if you integrate e to the power of 4x. You're going to get e to the power of 4x again, divide by the constant. So same here, now the constant is x, so we divide by x. And then finally the x and x cancels out, thus giving me this. So it is integrated, it's just that you integrate e, you get e again. So that's why there's no changes to that. Just remember that when you integrate with respect to y, your x is a constant. Your x is like a number there. I see. Okay, yes. So currently it's with respect to y. That's why it's a bit easier. If x, it will be a bit hard because you have an x here, you have an x here, would be harder. Okay, as for the class test, anyways, no worries. I will give you a trial on whatever method I'm using so you can upload some random images to check whether the uploading is okay or not. If any problem, you can communicate with me. So it won't be out of a sudden. Anyways, I'm going to stop sharing my screen now. Give me some time. I'm going to open the attendance. Okay, so let me share it again. Yep, here you go. How many more do we have? 4 more. Okay, so I don't think it is moving. Anyways, let me know after the class. I can also download the attendance sheet from the Teams. So let me download it as well. Is it not downloading because I'm sharing my screen for a while? Yes, okay. Download it. So anyways, let me know those who can't sign up for your attendance just now, or maybe you're absent, not sure. As for today, we are done. Again, let me think about it whether there are more parts I want to cover for chapter 2, but otherwise we're actually done with chapter 2. So I'll see you in our next class then. Alright, you guys are welcome. Bye-bye. Welcome, welcome, welcome everyone. Okay, I'm going to leave the meeting now.